So this is the first podcast in the unit on projectile motion, which is two-dimensional kinematics. And these first two podcasts are all about vectors, and I apologize ahead of time because it's all math stuff, so it's kind of dry. But it's also very important because we're going to be using vectors a lot in this class from henceforth. So the objectives for this, you will be able to compare and contrast scalars and vectors. Not a lot of objectives for this part. So definitions: a scalar provides information about how large a measurement is. It gives one item of information, magnitude. So it only gives magnitude. So speed would be an example of vector quantity because you only say I'm traveling at 45 miles per hour. Temperature is also a vector. Time is a vector. You don't say you're traveling, or you don't say, somebody asks you the time, you don't say it's 12 o'clock north. So it just gives only a magnitude. Vectors provide information about how large a measurement is and the direction of the measurements. It usually comes like in an ordered pair of numbers. You're not really worried about this. This is higher level math stuff. But example of vectors would be velocity. I use speed for the scalar. Velocity is a vector because if I ask for the velocity of something, I want the magnitude, which can be in miles per hour, but I also want a direction, be north. So other examples of vectors could be acceleration, forces are vectors. We're going to do a lot with forces in the next unit. So these are the major ones that we're going to be working with. But got to remember, it's a magnitude and direction. Magnitude and direction. If you've ever seen Despicable Me, the little guy in the yellow spandex, his name is Vector because he's committing crimes with both magnitude and direction. So that's important. Write that down. Magnitude and direction. Scalar, only magnitude. Oh, vectors in multiple dimensions. So the process for adding vectors works even when the vectors do not point along the same straight line. So you can add vectors that look like this. You can add vectors that look like this with a little bit of help from our friend trigonometry. So if you're solving one of these two-dimensional problems graphically, you'll need to use a protractor. Don't worry about that. We're just going to do it all mathematically. But you can do it graphically by drawing the vectors at the correct angle and also measuring the direction of magnitude. So you take your graph paper, draw your vectors, and you can find out its y component and its x component. All vectors have two components. Even if they're a straight line, they still have two components. So you can add vectors by placing them tip to tail and then drawing the resultant of the vector by connecting the tail of the first vector to the tip of the second. That will be for another PowerPoint. So the figure, where's it at? There it is. So the figure below shows the two forces in a free body diagram. We'll get to free body diagrams when we talk about forces. So if you move one of the vectors so that the tail is at the same place as the tip of the other vector, its length and direction do not change. So what we did here is the original vector was right here. And all we did was slide the tail of this guy, we just slid this guy over so its tail matched this guy's tip to tail. I don't know if this video will play, but we can see. Yep, cannot open specified file. I didn't think it would. So vectors in multiple dimensions again. If you move a vector so that its length and direction are unchanged, the vector is unchanged. Even though we slid that guy to the right on the previous slide, the vector was still the same vector. Like this guy right here is the same as this guy right here. We just moved it over a little bit. Totally legal. So you can draw the resultant vector pointing from the tail of the first vector to the tip of the last vector and measure it to obtain its magnitude. So what we did there, here is the one vector, here's the vector we slid. So you can draw the resultants, which I'll do in blue, from the tail of the first vector, so the tail of the first vector, to the tip of the second vector. This is adding two vectors together. You're going to end up with this resultant vector. resultant vector. It has an x component and a y component, which come from the other two vectors. And since it's a vector, you're also going to have to figure out this angle. You can use any of your trig functions to figure out what that angle is. And I really doubt this movie's going to play, but yeah, I don't know why these movies never play in this. Oh well. So symbolically, we shall denote vectors in uppercase, boldface type, or uppercase with a line over it. So you can either see them in bold. I think your book uses the bold more. I like to use the line when I'm doing it on the board. It's easier to see. So boldface, or they just put a line over it. Like that's how I'll do it if I do a problem on the board or a problem in PowerPoint or something. All our scalars will be real numbers and will be denoted in uppercase italics type. So if it's just a scalar, it'll just be like, an italic B. It's a little more slanted. So the vector length of 0 is called the 0 vector and is denoted by 0. So we just have a point that's still a vector, and it's just a 0 vector. You can pause there and write the other stuff down if you want. Don't worry about that too much. Alright, so definition of a vector. If v and w, here's your v, here's your w, are any two vectors, then the sum v plus w is the vector determined as follows. You position w so that its initial point coincides with the terminal point of v. So the initial point of the vector is the side without the arrow. So we want to take w's initial point, which is right there, and have it coincide with the terminal point of v. The terminal point is where it ends, so that's where the arrow is. So basically we put the tail of w on the tip of v. So we're going to get two vectors added together looking like this. The vector v plus w is represented by the arrow from the initial point, so the initial point of v, and we draw it to the terminal point of w. Do that in a different color here. So this is your resultant vector. When you add two vectors together, you get another vector. V, w, v plus w looks like that. There's also something called the parallelogram method. So if you can see here, here's a nice parallelogram. So how we did that was we slid v over, so its tip here matches the tip of w. We slid w down, so its tail and the v's tail were together. You get a nice parallelogram. And the resultant vector is formed by just drawing the line between two opposite corners. So v and w are any two vectors, then the difference of w from v is defined by like this. So v minus w. So negative w looks like this. W is going this way. All you have to do is it's v minus w is change it to v plus a negative w. Flip w around the other way. So here's our original w. But we want to do v minus w. So we had to flip this guy going the other way. And we did the parallelogram method because now this guy's gone. We still have v, we still have w. And we slid w up here, tip to tail method. And you get a nice resultant vector, which is v minus w. Told you, very dry. Another definition, if v is a non-zero vector and k is a non-zero real number, which is also called a scalar, then the product of kv is defined to be the vector whose length is the absolute value of k times the length of v, and whose direction is the same as that of v. So the direction doesn't change, just the length's going to change. It can also flip which direction it's going in. So if you look at here's our original vector v. If we do 1/2 v, you see it decreases by 1/2. If we do 2v, you see it gets twice as long. If you do negative 1v, it's the same size, but just flip the other way. If you do negative 3v, it's 3 times as large, but pointing in the opposite direction. So a vector of the form kv is called a scalar multiple. So in this figure right here, V has been positioned so that its initial point is at the origin. It's how we always want to draw these things. Makes it a lot easier. Draw your first vector starting from the origin. Makes it a lot easier. So the coordinates of the terminal point V are called the components of V. So let's say this was 4, this was 3. So the components of V would be 3, 4. So choosing a coordinate system, such as this guy right here, is similar to laying a grid on a sheet of transparent plastic paper on top of a vector problem. So you have to choose to put where the center of the grid, the origin. You can pick the origin wherever you want. It's usually a good idea to start like the tail of your first vector right at the origin. So if I just had any old random vector, I'd want to start here. Let's say it's ending right here. So we draw it like that. And you can see that if I draw these dash lines in here, even though this is just one vector, this original guy I drew, sorry if it's not very straight, you can see it's made up of a vector that's only in the x direction and only in the y direction. Two different vectors, because we did tip to tail. Here is a resultant vector of these two vectors. So we can break any vector that's at an angle into x and y components. This one's easy to see. It's 1, 2, 3, 4, 5. So its x component is 5. Its y component is 1, 2, 3, 4, 5, 6. So those are the components of the vector. Now we can find the length of the vector, Pythagorean theorem. We can find theta using trig functions. I know, you're excited. Try to contain it, please. So when the motion you were describing is confined to the surface of the Earth, it is often convenient to have the x-axis point east and the y-axis point north. So that little compass rose I've been drawing on the board, you should always do this. If something's moving up and down, and then it's usually convenient to put up as positive and down as negative. So what I just said, when the motion involves an object moving through the air, positive axis is usually horizontal and the vertical right here. So this would be positive, positive, negative, negative. Sometimes motion will be on a hill. We'll do some problems with forces that are on ramps. We'll have like a box on a ramp. This is why physics is cool, because you can pick your axis to be anything you want. So it's convenient to have the x-axis going up the hill and to have the y-axis pointing perpendicular to the hill surface. So then we can rotate this guy. Here's our box. Here's the x-axis. So it's still on a hill. We just rotated the hill a little bit. See, it's a little easier to work with if we choose the coordinate system like this over here. Then we can just rotate it a little bit, and we're all good. Thank you for bearing with me through that one.